All right, so now we can extend this into what our central limit theorem says is that it doesn't just have to be a normally distributed random variable. It can be any random variable, okay? If any random variable has a mean u and a standard deviation sigma, so it could be discrete, it could be continuous, okay? Well then, if the sample size is large enough, then the sample mean from that distribution will also be normally distributed, all right? So in other words, the mean of the sample size is equal to mu, the standard deviation will still be sigma on root n. So whilst in the last exercises we spoke specifically about sampling from a normal distribution, our central limit theorem tells us that we can actually sample from any distribution, providing our sample size is big enough. And typically, as long as our sample size is larger than 30 is enough, all right? So here's just a continuous random variable, okay? It has a distribution with probability density function given by, find the probability that the average amount of coffee contained in 25 randomly chosen cups will be greater than 173 mils. So we're going to pour the coffee machine 25 times and work out the average number of mils in each cup. And we want that to be greater than 173. So we know from our central limit theorem that the mean and the standard deviation of this particular distribution are significant in the mean and the standard deviation of the average value of the cup. So first things first, the mean of this distribution, remembering from our continuous stuff, the mean of a continuous distribution is x times p of x still, between 160 and 180, x times f of x dx, and I get 170. Straight onto the CAS. Variance, e of x squared minus e of x all squared. E of x squared is x squared times f of x dx. So 160 to 180, x squared times f of x dx, minus e of x all squared. So if I work out that integral first, that integral in green comes to 28,993. E of x squared is 170 squared. If I work out that total, might as well use red, I end up with a standard deviation of 5.77. Okay, so that's what the standard deviation of that particular continuous distribution is. So now, if I want to look at the probability of my average cup, the average of the 25 cups being greater than 173 mils, well, it's going to be normally distributed. I want it to be from 173 to infinity. The average, the mean of this distribution is 170. We work that out over here in the first part. The standard deviation of this distribution is my 5.77 over the square root of 25 because there was a sample of 25. And that gives me 0.0045. So what that tells me is that the probability of the average amount of liquid in each of those cups as a sample, the average of the sample being greater than 173 is very small, 0.0045. All right. Similarly, if we've got a binomial variable with parameters n and p, again, as long as my n value is suitably big enough, the same conditions apply. The sample will be normally distributed with mean mu and a standard deviation of sigma on root n. So if 15% of people are left-handed, use a normal approximation to the binomial distribution to find the probability that at least 200 people in a randomly selected group of 1,000 people are left-handed. So I've got 1,000 people, p is 0.15, sample of 1,000, my expected value is 150. Okay? My standard deviation, my variance, sigma squared, is equal to n times 1 minus np 1 minus p, which gives me 127.5. So that's my variance. Okay, so this part of it here, I guess, slightly different to what we had previously, because in this one here, we're using a normal approximation to the binomial. So what we're saying now is a little bit, this is almost like a methods question in reality. What we're saying is that my distribution, my variable is distributed as 150, 127.5. So in actual fact, in this case, the difference is my standard deviation. My standard deviation isn't the square root of 127.5 on n, or isn't sigma on root n, I should say, because we're using a normal approximation. We're just going to, what we're doing here is we're working out that that probability is 0.3 zeros, 5 zeros and a 5. What we're doing really here, it saves us from having to do, undo that. It saves us from having to do binom CDF. What do we do? We've got 1,000 trials. Probability of success is 0.15, and I want from 200 to 1,000. Okay, that's what that is an approximation to. All right, so it's a slightly different question. Okay.